Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
This is one of the most misunderstood topics in physics.
It governs everything from molecular collisions to humongous storms.
To see the confusion around this topic, you only need to ask yourself one simple question. What does the Earth get from the Sun?
I'd say light rays, heat. Oh wait, Mumbai ki garmi.
Literally.
Also a nice tan, vitamin D, and some energy.
Precisely. Every day, the Earth gets a certain amount of energy from the Sun, and some of that energy is radiated back into space, while some of it is retained by the Earth due to greenhouse gases. So, the amount of energy coming in is equal to the amount of energy going out. So, what do we really get from the Sun?
To answer that, let's back up a bit, as we usually do. In the winter of 1813, France was being invaded by the armies of Austria, Prussia, and Russia. I know it sounds very similar.
Rolls of the tongue, right?
I swear. So, over there, one of the son of Napoleon's generals was Sadi Carnot, a 17-year-old student. On December 29th, he wrote a letter to Napoleon to request to join in on the fight. But Napoleon, preoccupied in battle as always, never even replies. But Carnot gets his wish a few months later after Paris is attacked. The students defended a chateau just east of the city, but they were no match for the advancing armies, and Paris fell only after a day of fighting. Forced to retreat, Carnot is extremely devastated.
So, 7 years later, he went to visit his father, Lazare Carnot, who had fled to Prussia after Napoleon's downfall. His father was not only a general, but also a physicist. But what kind of general was he? I mean, he fled.
Yeah.
So, he wrote an essay on how energy is most efficiently transferred in mechanical systems. There, in Prussia, the father and son duo spoke about the biggest breakthrough of the time, steam engines. They were already being used to do all sorts of things, from mining ore to powering ships. It was clear to both of them that the future industrial and military might of nations depended on having the most efficient steam engines. But French designs were falling behind those of other countries like Britain.
So, Sadi Carnot, the proud Frenchman that he was, took it upon himself to figure out why. At the time, even the best of the best steam engines only converted 1% to 3% of all thermal energy into useful mechanical work. If he could improve on that, he could give France a huge advantage and restore its place in the world.
So, bro spent the next 3 years working on that. Then he acted kind of like Schwarzschild
If you know, you know.
because he imagined a scenario that was suitable for him. He took an ideal heat engine, which would entail no losses to the environment and no friction, and he used a piston, a hot bar, a cold bar, and some air to create this ideal engine. In his mind, by the way, he never did actually make it because it's practically impossible.
Yeah. And now, you would expect an ideal engine to have 100% efficiency, right?
Yeah, exactly.
But this still wasn't perfectly efficient. Rather, it was only 27% efficient. When William Thomson, also known as Lord Kelvin, name sounds familiar, right?
Yeah.
He looked at Carnot's engine and he realized that the engine would only be 100% efficient if its lowest temperature was 0 Kelvin. It is that temperature at which all molecular movement stops. Although we have reached temperatures of the order of 10 raised to negative 10 Kelvin, reaching this temperature of 0 Kelvin is practically impossible.
This is because the formula for the efficiency of a Carnot engine is 1 minus Tc over Th. Here, Tc is the temperature of the cold bar and Th is the temperature of the hot bar. So, in order to have 100% efficiency, you can have two options. Either the temperature of the hot bar would have to be infinite, because anything over infinity is 0, or you can have 100% efficiency if you have the temperature of the cold bar to be exactly absolute 0, because 0 over anything is 0.
True.
Thus, energy has to spread out or radiate out of the engine, while it's being used.
Since the spread out energy is not as useful as Arnav on a good day,
Haha, wait a second. As if you don't do any time pass.
please, we can surely say that the energy is most useful when it is concentrated and least useful when it is spread out.
So Rudolf Clausius, another dude, came up with a way to measure how spread out the energy is. He called it entropy. Entropy is a measure of disorderness of a system. For example, let's take a Rubik's Cube. A Rubik's Cube is more ordered when each face has the same color, but quickly becomes disordered when the faces are turned and the cube is scrambled.
Another example that we can take is basically to do with paints. Blue paint mixed in with red paint is more disordered than a blue bottle and a red bottle separately. Another one is about a gas. A gas is more disordered than a solid at a room temperature because its atoms move randomly, whereas those of a solid are regularly arranged. And we know less about the positions of the gas atoms than we know about the solid atoms, of course.
Exactly. So, have you ever wondered why a glass of cold water placed in a warmer room heats up?
Not really.
It's because energy spreads out and tends to flow from a higher temperature to a lower temperature until both of them reach a constant temperature called thermal equilibrium. It's not that energy always flows from high to low temperature. It's just so unlikely to happen that it basically never happens.
This can be explained by the statistical view of entropy. Suppose we have 4 coins. Obviously, each can show either heads or tails when they are flipped. One possibility is that all 4 are heads, or maybe 3 are, or maybe 2, maybe 1, or maybe 0. You get the idea, right?
Yeah, this is called a system. It can be described with the number of heads that can appear. As said before, it can be anything between 0 and 4 inclusive. Thus, our system can be described by 5 macro states. For each macro state, there are micro states that give the number of different arrangements possible for that to be possible. Basically, if you know nested loops in computer science, it's like that.
Yeah. The notations for microstates is omega. So there's a simple formula to calculate the number of possible arrangements rather than counting each one by one. Just take how many possibilities are there on each coin, which is 2, raised to the number of coins in our small system,
which is 4.
So 2 raised to 4 gives you 16 possibilities.
So the scenario that we mentioned earlier, heat flowing from a cold body to a hot body, is not really impossible. It's just that probability says
nahi hoga.
It's basically forbidden by a special law of physics called the second law of thermodynamics. It basically states that the entropy of the universe always increases. So back to where we began. What do we really get from the sun?
We answered light rays, heat, Mumbai ki garmi, a nice tan, vitamin D, and also energy. But of course, the only correct answer here is garmi. I mean, oh my god, it's just
literally,
too hot.
Literally too hot.
But we forgot the most important thing, which is one of the essentials for life. It's something which we like to call entropy, which we earlier discussed. Remember how we mentioned that spread out energy is useless and energy is most useful when it is concentrated and least useful when it is spread out? This is also applicable here.
So, the energy that we get from the sun is extremely concentrated into packets of energy called photons. Plants use this energy for photosynthesis, and obviously the whole food chain is dependent on it. And as this progresses through the food chain, this energy becomes slightly lesser and lesser useful. Since the energy of the universe is always increasing, and we need energy in a more concentrated form to survive, it really does sound like entropy is this awful thing that leads us inevitably to the dullest outcome imaginable.
But just because maximum entropy has low complexity, that doesn't mean that low entropy has maximum complexity, right? It is actually in the middle where complex structures like us, human beings, can appear and thrive. So let's make use of the low entropy that we've got.
While we can.